So good afternoon, my dear friends. This is Mario Leo Joseph from the Department of Chemistry, Sacred Heart College, Autonomous, Tirupattur. And this is a video for the third BSc Chemistry students of Sacred Heart College, Autonomous, Tirupattur, which is going to speak on the concept of hyperconjugation in organic molecules. During the previous session, I think we spoke of how to write organic molecules. So the next thing that we will be seeing is we'll be going into understanding why the structures are, in a zigzag fashion. So this is a picture of a stick model that we have taken. So this is the side view of the stick structure, and this is the aerial view of the same stick structure. So here what you're seeing is, so this is going to be the carbon. So you're having one carbon here, second carbon here, the third carbon here, and the fourth carbon here. So this is, and there's a fifth carbon here. So this is the structure of N-pentane. So I'm having 1, 2, 3, 4, 5, 6. So I've represented only the hydrogens in between the end carbons. So I've not mentioned the hydrogens here. So the black line that you're seeing here is the carbon chain, and the red ones that you're seeing are the hydrogens. But why was not the CS3 mentioned is not our point of discussion today. Our point of discussion today is to speak on why these hydrogens are pointing in the downward direction, while these hydrogens are pointing in the upward direction. Look at this arrangement here. Again, you are seeing that in the zigzag structures, the two hydrogens are pointing in opposite directions. So why is this happening in the case of organic molecules? So that is a point of discussion today. So you can see that in this aerial view that there are two hydrogens that have been pointing downwards, and here you can see that in the next carbon the same hydrogens are pointing upwards. So that is a point of discussion as of now. Okay, so why is this happening? So this is because of hyperconjugation. So what is hyperconjugation? So to be very, specific, very specific, there is a electron density from a bonded molecular orbital which moves into a nearby antibonding molecular orbital, which gives the bonded molecular orbital a more amount of space, stabilizing the molecule. So this would be the definition of, hyperconjugation. So what is this? Now, let's have a look. Now, before we, go into what is hyperconjugation, we need to understand that the theoretical aspects that bonding molecular orbitals, anti-bonding molecular orbitals are all real representations in molecules. They are not, just for the sake of saying things. Now, this is the structure of your methane. So you're seeing a structure of your methane. Now, this particular, white orbital that has been mentioned is the anti-bonding molecular orbital for this particular hydrogen. So this is a carbon-hydrogen bond, which we call as a sigma bonding molecular orbital, as to our understanding. So the opposite end, you have the same carbon-hydrogen bond, sigma star molecular antibonding molecular orbital. So where are these molecular orbitals present? They are present in all the molecules. So that is our understanding. So if you're going to look at, this particular bond here, the second bond here. So maybe I'll use a different color for that. So here you see a second bond here. So this particular carbon hydrogen bond is going to have its, will have its sigma star here. And similarly, what you will be seeing is this particular carbon hydrogen will be having its sigma stars in its opposite end, and vice versa. This carbon hydrogen will also be having its sigma star in this particular direction towards you. So all the carbon hydrogen sigma bonds will be also having what? Will be also having their sigma star molecular orbitals. So this is our basic understanding. Now, now look at this particular molecule. So this is a molecule where this is a molecule of ethane. So it is showing you Newman projection. So we'll be coming to the representations of Newman projection on a later stage in the next video, perhaps. Now, here, just for our understanding sake, you can look at this particular, these two structures at the bottom. So these two are Newman projections, as I told you. So this is a staggered projection, and this is a eclipsed Newman projection. Now, here the hydrogens in the carbon, there are two carbon hydrogen bonds, and both the hydrogens are right behind the other. One is behind the other. However, here in this case, you can see that this particular hydrogen, this particular carbon hydrogen has the backward carbon hydrogen is at the opposite end. So this is just the opposite. So this hydrogen is down here. However, here both the hydrogens are right behind each other. Here they are at the opposite ends. So we are calling this as the staggered structure, and we are calling this as the eclipse structure. But at the beginning, I told you something. So what is hyperconjugation? So I told you that a carbon hydrogen sigma bond, to be more specific, a carbon hydrogen sigma bond, if it finds or if there is a carbon hydrogen's antibonding orbital just adjacent to it, it is able to donate the electron density from the bonding molecular orbital into the nearby atom's antibonding molecular orbital, giving it more space for the bond pair of electrons to exist, thus reducing the energy of the molecule, making it more stable. No. In the first case, as you saw here, you can see that both the hydrogens, so this carbon hydrogen, we call it as a sigma molecular orbital. Same way in vice versa, this carbon hydrogen's sigma star is below here. So you can see the sigma star is here. However, you can also see that the next carbon's hydrogen, there is a sigma, right? So there is an eclipsing of the sigma molecular orbital with a sigma molecular orbital. So a bonded pair of electrons are being, you know, next to or adjacent to the adjacent carbons. Bonded pair of electrons are nearby. However, if you look at the last structure, the carbon hydrogens, antibonding orbital is right below here as indicated in this structure, but the hydrogen has been brought down. So what has happened is this particular carbon's sigma orbital is now overlapping with the sigma star orbital. So this is what I was saying. So what happens is when a sigma molecular orbital is overlapping with a sigma star antibonding orbital, the sigma molecular orbital uses up the empty space in the sigma star antibonding orbital, thus reducing the energy of the molecule. So this is what you see in the last diagram. So you can see that the sigma CH is overlapping with the C sigma star. Now this is possible only when the hydrogens and the carbons are the carbons on the hydrogens are in this fashion. So you can see that only if they are in a zigzag fashion with the hydrogen and the hydrogens are like this. Now you can see that the this particular carbon hydrogen bond. So this will have its antibonding molecular orbital here, so it will be able to overlap with this, and automatically the other side, this particular hydrogen here, or this particular hydrogen, it will be having its antibonding molecular orbital in this particular direction, so it will be able to overlap with this hydrogen here. So this particular zigzag structure is because of the staggered conformation of the organic molecules, which is brought about because of hyperconjugation, which is causing a stabilizing effect in the molecules. So this is the reason why we use kings in carbon atoms and we write the structure as zigzag molecules. I hope you understand. Thank you.